Hi everyone, I'm Greg Mack. After I got my PhD in astrophysics, I was a professor of physics and astronomy at a small university for a while. My career path has since taken me to different aspects of physics since then, but when I was a professor, and even a bit after that in this next career path, I did a number of videos regarding physics and physics-related things, talking about physics concepts, things like that. And so, as the academic year is starting back up, I was thinking about that and was kind of inspired to start doing that again. And so I wanted to start talking about physics concepts, math concepts, kind of thinking about sort of intro physics-like things, and wanted to share that. And so I figured as a warm-up, I would start talking about probability. And because probability actually features in a lot of different parts of physics. In the higher levels of physics, it's really involved with quantum mechanics, statistical mechanics and thermodynamics, stuff like that, where you have a lot of different particles, a lot of chances for things. And so I thought, why not just start off talking about that? It involves math, it gets getting used to numbers, but not so much the physics concepts yet. So just talking about probability. And if you're like me, you like games, and I have a lot of dice around just because I do like playing games. And so why not talk about probability in terms of dice? Get thinking about numbers, maybe get some of the rust off some of that mathematical thinking, right? So let's talk about dice and probability. So let's say you had a six-sided die. So you had the numbers 1 through 6 on a cube like this, and just you always have a chance to roll numbers whenever you roll that die. So let's start thinking about what that probability means for rolling specific numbers on a six-sided die. So when you have six-sided dice, right, you have the numbers 1 through 6 on all the different sides. There's an equal chance of getting any of the different numbers, right, assuming your dice aren't weighted for some strange reason. So if you're trying to figure out the probability of rolling a specific number, let's say the number 6, then what that is the possibility of, well, just one outcome, because you're looking for one specific outcome, divided by the total number of outcomes. So on a six-sided die, there are 6 different outcomes. So that total outcomes number there in the denominator is a 6. So the probability of rolling a 6 is 1/6. You have a 1 in 6 chance of rolling a 6. You also have a 1 in 6 chance of rolling a 5, a 4, a 3. They're all that same because they all have equal probability on that evenly weighted die. So if you think in terms of percentages instead of fractions, then what that is, it's about a 17% chance that you're going to get a 6 or any other specific number. So what if you're thinking about not rolling a 6? Well, first of all, think about this in the big picture of what it means to be rolling the die, is that all the different outcomes have to add up to 100%, right? So, because you're going to get a number. So you're 100% going to get a number when you roll the die. So unless there's some weird thing where it lands on a corner, which isn't going to happen unless you're not using the right kind of surface, right? So 100 minus 17 is 83. So the answer we should get here for anything that's not a 6 should be 83%. So let's see if we get that. So when you have all the numbers, all the different possibilities in one thing like this, they're all part of the same system. And so they're all dependent on each other. And so when you have dependent probabilities like this, then what it means is that you have to add them together. Or that's the function you use, is that you add them together to get the answer that you want. So that means that you have the probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3 plus the probability of rolling a 4 plus the probability of rolling a 5. And again, we're doing that because they're dependent on each other. They're dependent probabilities. Okay? So we already know what each one of these are because it's the same thing up here, right? So it's 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. So that gives you 5/6. You have a 5 in 6 chance of rolling a number that's not a 6 on that die, and that's about 83%, which is exactly what we thought we were going to be getting. And again, that's because these probabilities are dependent, and you could add them together like that. So let's think about that dependent probability in one more way. So what if you wanted to roll all even numbers, for example? Or not all of it, but any even number on the die. Right? There are 3 even numbers, there are 3 odd numbers, and so you would think that you would get a 50% chance of even, 50% chance of odd. Let's see how the math makes that work out. Okay? So the probability of rolling any even number on that die is the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. And so, again, we're adding them because they're dependent on each other. They're all part of the same system, right? So that's 1/6 plus 1/6 plus 1/6, or 3/6, which is 50%. And so we got the number that we were thinking we were going to get. And that's all part of just one die rolling and thinking about the different possibilities involved with the numbers there. So, but then, what if, instead of rolling 1 6-sided die, you end up rolling 2 6-sided dice? So, what if you wanted to roll a 6 on one die and a 6 on the second die when you roll? What's the probability of that happening? Well, does the rolling of this die have any influence at all on the rolling of this die? As much as we'd like the answer to be yes, the answer is no, right? And so they're completely independent of each other. What you roll on the first one doesn't affect what you roll on the second one. So that's treated differently than for the dependent case we were just talking about, where all the different numbers are linked on one die. The numbers on both dice are not linked to each other. So the probability of rolling a 6 on 2 dice, 2 6-sided dice, the way that works for the independent probability is that you multiply them together instead of adding them. You need to multiply them. So you have the probability of rolling a 6 on the first die, and you multiply that times the probability of rolling a 6 on the second die. Okay? So again, we know what the probability is of rolling a 6 on one of the dice, so that's 1/6, and then you multiply that by the second probability, which is also 1/6, and that ends up being 1/36. So you have a 1 in 36 chance of actually rolling 2 6s when you roll 2 6-sided dice together, which also means you have the same probability of rolling 2 4s, 2 1s, etc. And again, if you think in terms of percentages instead of fractions, that's about 3%. So that's kind of, it's kind of rare that you would act in terms of all the dice rolling you could possibly do for these 2 dice, that you would get the same number. Okay. So now 6-sided dice aren't the only dice out there. There's 4-sided dice, there's 10-sided dice, there's a popular game involving 20-sided dice, and so let's talk about 20-sided dice. Just because it's a larger number, it's fun to talk about, why not? So let's do the same thing we were just doing for 6-sided dice and talk about it in terms of 20-sided dice. So let's start back at the beginning of what's the possibility, when you have a 20-sided die like this, of rolling a 20 on your 20-sided die. Again, they all have an even outcome as long as your die is not weighted oddly, right? They all have an even possibility of happening. And so that means that you have one specific outcome divided by the total possible number of outcomes, which in this case is 20. So that means that you have 1 out of 20 is the chance that you're going to roll a 20 on your 20-sided die, which is equal to 5%. Okay. So then again, what if you're not going to roll a 20? The probability of anything but a 20. And on the one hand, you could do it by 100% minus 5%, which is 95%. That should be the chance that you're going to roll anything but a 20. Again, let's apply what we just talked about before and see how that works out in this case. The probability of not 20 is the probability of everything else. And remember that we're talking about all these different numbers in the same system, the same object, they're all linked together. And so that means that you're going to be adding up all the probabilities for all the different numbers because they're dependent on each other, right? So that ends up equaling the probability of 1 plus the probability of 2 all the way up to the probability of 19, right? And so each one of those is 1/20th, and so adding them all up together means that you end up with 19 out of 20, or 95%. And so we do get the number of 100% when you add those together, which means that we're doing the math right? All right, so now there's another thing you could think about, just as another example, and that's what if you wanted to roll anything bigger than 10, including 10. So the probability that you're going to roll a 10 or above on this 20-sided die. Again, how do you think about doing that? All these different probabilities depend on each other because they're all in the same system. They're all in the same die, right? So that means that you're going to be adding them together. So the probability of 10 plus the probability of 11 all the way up to the probability of 20, right? And so there are 11 numbers there, and so you end up with 11 out of 20, or 55%, so you have a slightly better than 50% chance that you're going to roll a 10 or higher on the die. Of course, if I had said 11 or higher, we would be exactly at 50%. So having 10 or higher means that you have a little bit more probability of actually getting something that's in that range. So let's do one more thing with this 20-sided die and go back to thinking about what happens if you have more than one of them. So again, if you're thinking about two different 20-sided dice, again, as much as you want it to, the rolling of one does not influence the rolling of the other. And so the probability of rolling a 20 on one of them is independent from the probability of rolling a 20 on the other one. So let's figure that out. So you want to roll a 20 on both of the 20-sided dice. So that's equal to the probability of rolling 20 on the first die times the probability of rolling 20 on the second die. And again, that's because they're independent of each other, okay? So because the one die does not influence the other die. And so that's 1/20th times 1/20th, or 1 over 400. So that means that you have a 1 in 400 chance that you're going to roll both 20s on two 20-sided dice. And again, if you think in percentages as opposed to fractions, that's about 0.25, or that is equal to 0.25%. So, small chance. Now, on the flip side of that, that also is the same possibility of rolling 2 1s. So rolling 2 20s, or rolling 2 1s, or rolling 2 of any specific number is going to be a 1 in 400 chance, or a 0.25% chance of that actually happening. Now, there are some games that involve rolling 2 20s and taking the better number, or rolling 2 20s and taking the worst number. And so that's where this kind of probability would come in. And so you have a 1 in 400 chance of rolling 2 20s, and also a 1 in 400 chance of rolling 2 1s. So what about the chance of rolling just 1 20? At least 1 20 when you have 2 20-sided dice? Well, that's a bit longer and involved of a discussion, and so I'll go into that in the next video. But I hope that you've learned something in this little warm-up that I've been doing, getting some of the rust off of your mathematics skills if you hadn't thought about that in a while. And I hope that you'll come along with me in this exploration of physics concepts and math concepts.